Let's go on page 69 when we're done. Okay, so like a broken record here, since logarithmic expressions can also be written in exponential form, same properties that apply to exponents can be applied to expressions involving logs. So if you don't know by now that logs and exponentials are tied together, you really haven't been paying attention. Okay, these properties will allow us to manipulate these expressions or the functions themselves to be able to solve them or do other things for them, or the words that come up a lot, equivalent expressions, where they look completely different, but they would graph the same thing or whatever. That's a big thing for us. All right, so this is a review of some of the properties and the way we get to manipulate them. Oh, let me remind you back up here because we have more room up here. If I have x squared times x cubed, what does that give me? X to the power of 5. And we know that. That's like way old business, right? We've known that for a long, long time. So, but sometimes I don't think you realize, I mean, I know you know what you're doing, but how to like connect it to other things. You are multiplying two terms that have the same base. That base is x, so you add the exponents. So the multiplication results in some addition happening. So multiplication, addition are tied together. They're tied together with logs as well. So if I have the log, and so this tells me that it is a log. This is the base of the log. This is called the argument. Okay, it's the argument. The argument is xy. If the argument is something that is it's a product of something, I can split it into two logs with the same base and change it to addition. Or the other way, if I have two logs with the same base that are being added, I can change it to the log of the same base, but those two arguments being multiplied. So I can go in either direction. So here, if I have log base 2 of 5x, that can become log base 2 of 5 plus log base 2 of x. But again, you could also go the other way. It goes either way. Is your little multiplication property there, or the product property. Quotient. Okay, so when I divide two terms with the same base, I subtract the exponents, right? So division and subtraction are related. So same thing here. Log with base b, I have the two logs the same base, and that just becomes subtraction. Everything that is in the numerator has a positive log. Everything that from the denominator is going to have a negative log. And again, you can go in either direction here, depending on whether you're trying to expand or condense. Sometimes you're told what to do. Sometimes you need to know what to do whenever you're in the middle of stuff. Then the power property, which I did mention the other day. If I have the log of an exponential, then that exponent gets to come out front. And then that's how you get the variable out of the exponent. So if you look at this, I've got log base 7 of 3 to the x. Well, since that x gets to come out front, now I have x times log base 7 of 3, and that's just some value that you can get from the calculator. It's just a number, and then x is no longer up there in the exponents. Okay, all that sound familiar? Okay, should sound familiar. Just got to knock those cobwebs off. All right, so it says for each of the following, we are going to write an equivalent expression by condensing. All right, so this one's fairly straightforward. Two logs, they both have a base of 4. So this becomes log base 4 of x times y. Okay, you get to just multiply them. Right. Here, two logs with the same base with subtraction. So that's going to be log base 3. And then from the positive log, the 5 goes in the numerator. Z comes from the negative log, so it is in the denominator. Okay, everybody okay with that? All right, so now when we have more than one term and we're adding and subtracting and they're all logs, in the past, I've always kind of shown you the math behind it and how to be careful with your signs and this and that. I think most people get it, but then I think we then mess it up because we overthink things, because y'all are good at overthinking. So instead of all that, I'm just going to show you kind of the shortcut, and there is math behind it, but we're not going to worry about it because I think that's what leads to confusion sometimes. And it's really just applying this stuff, but you got to be careful with parentheses and all kinds of things. So here's how I suggest you do this, is that if you have more than two, or I mean, it doesn't really even matter. It doesn't matter how many you have, but if you're adding and subtracting, but there's at least subtraction in there, make sure the bases are all the same. So this is log base 10. And then since there's some subtraction, you know it's going to be a quotient. And then so you get stuff in the right place. You look back here. This log is positive. So its argument, which is x, goes in the numerator. This log is negative. So that 5 goes in the denominator. This log is negative, so the z goes in the denominator, and then we're done, and everything's in the right spot. Okay. Any questions about that? Because it really is fairly straightforward there. Okay, but before you do that, you have to make sure that there's a log, that there's nothing being multiplied in front of the log. So if you look at D, you see I have that 3 out front. I can't start by making myself a little fraction bar. Instead, I have this 3. It's not an equation, so me dividing doesn't make any sense. And even if it was, then I'd have to divide that by 3, so that's a mess. But I can bring this up and let it be an exponent. So this becomes log base 2 of x cubed minus log base 2 of y. Okay, that's where your little exponent comes from. Now I have 2 logs of base 2, so it's going to become log base 2. There's some subtraction, so I have a fraction bar. The positive log is x cubed, so that goes in the numerator. Negative log has the y. There we go. Okay. Any questions at all? All right, I want you to work on E. You can talk about it amongst yourselves. So I first need to do that, right? Got to make all those constants or those coefficients there into exponents. Then I've got log base 7. Okay, a squared, it comes from a positive log, so it goes up top. B to the 5th comes from a negative, so it goes down in the bottom. 4 is positive, so it goes up top, and I'm going to put it in front. If you have a squared times 4, it's not wrong. Just the proper way to do it is to put the number in the front. Okay. Any questions at all? We're all good? Can do that? Beautiful. Now let's look at F. So here we've got a little bit of a problem because our instructions say condensing each expression to a single logarithm. Well, all the rest of those were just fine because they all had logs. I was putting logs together. Well, here I've got a log, and then I've got this constant right here. That's not a single logarithm, so I have to make it into a single logarithm. That means I need to represent 2 as some sort of log, and not just any old log, but it needs to be a log base 6. So for me to figure out what to do with this, I'm going to have to say that 2 needs to equal log base 6 of something, but I don't want to use x as my something because there's already an x there. I don't want to confuse it. So I'm going to use y. So I should be able to rewrite this where I can say instead of 2, I can put log base 6 of something, but I got to figure out what that something is. So now that I'm here, though, I can rewrite this in exponential form. So if I rewrite this in exponential form, the base of the exponential is 6, and that would be 6 to what power? 2. So 6 to the 2nd power equals y, right? So what does y equal? 36. So that means that 2 equals log base 6 of 36. Everybody with me so far? That's how I figured out. These are equivalent expressions to, this has the same value as 2, but it's in the shape of a log. Now I'm not done because I didn't actually use what's up there. All I'm doing here is I'm replacing that 2 now. So instead of 2, I have this. So instead of that 2 right there, I have log base 6 of 36 plus log base 6 of x. Right? 2 logs, same base. So that'll give me log base 6 of what? 36x. Okay. What questions do you have? Anything? So what I did in green there, I had to do to rewrite the 2 in a log expression, then put it back in here and put it together. Okay. Any questions at all? All right. Now let's look at example 2. Before we worry about what it is, let's first talk about, well, let's just look at this. It says, which of the following expressions is equivalent to this? All right, so before I even look at my answer choices, I'm going to look at this. I've got log base 3 of x squared over y. I'm just rewriting it, so just rewrite it first. Now we know we have an exponent rule, right? So that 2 could come out front. So if I have 2 times log base 3 of x over y, are these equivalent? Is what I just did actually legal? Yes or no? No, why not? The 2 only goes to the x, right? And so these are not equivalent. What this would have to look like, this would have to be log base 3 of xy with the 2 on the outside. If the 2 was on the outside, then it would equal that. You see the difference there? So you have to be careful about willy-nilly throwing your exponents out. What I need to do before I can pull the exponent out front is I need to actually rewrite it as log base 3 of x squared minus log base 3 of y. Now, because my argument, the exponent goes to the entire argument where it didn't here, now I can bring the 2 out front, and when I bring that 2 out front, that gives me C. Okay? What questions you got? We good on those? Yes. Okie dokie. All right. So then, let's flip this over. Okay, so the function f of x equals log of 6x. This is a horizontal dilation of g of x. And if you look at that, it's just stating the obvious, right? If I start with just log of x, and then I put a 6 in there, that is a horizontal dilation. Is that a stretch or a compression? That's 6. Compression, because x is a liar, right? So it actually shrinks it, even though you would think it would get bigger. Okay, so if I have this, but this dilates it by 1/6, okay? And it says, show that f can be rewritten, or also be written, as a vertical translation of g in this form. So if you recall, when we did exponentials, because that was before Christmas, we took some in one form, and then we kind of manipulated it, and we changed horizontal translations into vertical dilations and vice versa. So these are changing horizontal dilations into vertical translations. So it's the opposite because they are inverses of each other. So we're going to start off, I'm just going to start by rewriting that. So I've got f of x equals log of 6x. And what is the base of this log? 10. Okay. Well, then I know from my log properties, really the only thing I know that I could possibly even do right here is to split these up. So that would give me log of 6 plus log of x. Okay. Everybody okay with that so far? Then here, I'm just going to bring down some stuff. F of x is f of x. Log of x, what else can I represent log of x with? What does it equal? G of x. And I'm trying to get f of x is equal to g of x plus k. And k, that always just represents some constant. Isn't this just a number? Like, you don't know what the number is, but it's a number, right? And so this is your k. So f of x equals g of x plus k. We have that right here just by splitting that up. So my function, f of x, to put it in the right form, this would be g of x, that's my original, plus log of 6. So this, because I'm adding it afterwards, this is a vertical translation. started off as a horizontal dilation, manipulated it, didn't change the value of anything. If I was to graph this and graph this, they'd be the exact same thing. Okay. What questions do you have? Anything? Okay. All right, next thing is the change of base property. And that cheesy little video we watched the other day referred to this, but he made it sound like we only do it so that we can use the calculator because calculator only has log base 10 on it. That's not the case. I mean, yes, you can, and it does make, you can do that easier, but it does, you don't have to change it into log base 10. You can change it into any base you want. So if I have log base b of x, and I need, for whatever reason, if I'm trying to solve a problem or if somebody's telling me to put it this, and I have log base 6, but I need log base 2, whatever, then I can change it. I can make, as long as the numerator and denominator, the bases are the same, I can use a could be anything I want it to be that's legal with the log. And then the argument of the numerator is the same as the argument of the original, and the argument of the denominator is the base of the original. Okay, where all the same things have to happen. A is greater than 0, and a cannot equal 1. This goes on to say that this property illustrates that all logarithmic functions are vertical dilations of each other. So you know when I draw this little thing and I go, all right, well, we had a vertical dilation of 5. Does it really change my function? I mean, it changes it, but it doesn't change the way that looks because all of them are just stretched this way, just like exponentials are going the other way. Okay. So we're going to do the same kind of thing we did up there, all right, where we're just going to rewrite things. So I'm going to start with, well, okay, let's read this. It says, let f of x equal log base 4 of x, g of x equals log base 9 of x. We're going to show that f is a vertical dilation of g by finding the value of k such that this is true right here. Okay, so just like on the other one, we're going to start by just writing down f of x. F of x equals log base 4 of x. All right. Well, I need f of x to equal some number times g of x. G of x has a log base 9. So I need this to be in base 9. Does that make sense to you? That's where I'm going to use this right here. Right now, b is 4, x is x. So I want log base 9. So I'm going to make log base 9 in the numerator, log base 9 in the denominator. Because again, I can make it whatever base I want right now. Then the argument that is here in my original is the argument of the numerator. And the base of the original is the argument in the denominator. Okay. So a couple of things before we move forward. I want you to, number one, understand that what I just did was the change of base. I could have made this log base 5 if I wanted to, any base at all, and that still would have been x and 4 right there. I chose 9 because it's in the question. We all okay with that? Okay, everybody good with where it came from and why I chose what I chose? All right, so now what I'm trying to do is I'm trying to get f of x to be some constant k times g of x. G of x is log base 9 of x. Do you see that in the numerator right there? My numerator is log base 9 of x, right? So it's g of x in the numerator, I got something in the denominator. I can rewrite this that has nothing to do with logs. This is just basic number fraction properties. You can rewrite this as 1 over log base 9 of 4 times log base 9 of x. You see how I just split my fraction? That if I want to think about this being over 1, right, then I would just multiply them back together and get back right here. You with me on that? Okay, everybody good so far? Ask me a question. So all I did here, so look at this and see how you can go backwards. If I multiplied these two together, I would get this back, right? So basically, I'm just taking the constant part out of it so that this is going to be like a fraction in front of it. It's like doing this. Like all I really did, let me say it this way. If I have x over 2, that's the same thing as 1/2 times x. Would you agree with that? That's exactly what I just did there. It just looks weirder because of the logs. Okay, but exact same concept is all I did right there. Now, remember, this is what I'm trying to make happen here. Well, I've got f of x right here. Okay, I've got g of x. G of x is log base 9 of x. This is g of x. It's being multiplied by this number. That's just a number. There's no variables in there. This is k. So look, I do have f of x equals k times g of x. It's asking me to find the value of k. K is 1 over log base 9 of 4. Ask me a question. Let it process for a second. We don't do change of base a whole lot. Of all the log stuff, that's probably what we do the least, but that doesn't mean this couldn't be something you'd be asked to do. Any questions at all? We're all good, you think? Okay. All right, now the natural logarithm, which we did talk about the other day. Natural log, logarithm with base e is called the natural logarithm. And then we have this. This, you will never see it written like that unless it's being explained like this. Unlike the 10 where you can write it, but it's weird, but you don't have to write it. Here, you just wouldn't write it like that. You write it, and that is a lowercase l and an n. ln, not a capital I. It does not change the way any of the properties work, right? So I want you to look at example 5, see if you can figure out what the answer is, and then we'll talk about it. Okay, I heard somebody say 25% chance. Do y'all agree with that? I mean, you guess one out. If you had to guess 1 out of 4, you got a 25% chance, right? Can we up our chances a little bit before we even overthink it? I have 2. Do I have 2 logs with the same base? Yes. And there's subtraction, right? And we know that is going to have to change to what? Division. So that eliminates these 2 right away. Okay. So now I got a 50-50 chance, right? And then these would have to become exponents up here. So that would actually be the natural log of x cubed minus the natural log of y to the 4th. And so then when I subtract them, I get a. Okay. Any questions at all? We good? All right.